Hello, we're going to be talking today about alkene hydrations with different reactions. So let's get started. So we have an alkene here. And this particular alkene is tri-substituted. Notice that this carbon here has two substituents, so in place of the hydrogens, and one here. So it is tri-substituted. And that will be important because alkene hydrations, say that we do that with just diluted sulfuric acid, so we have hydronium here. What that happens is the reaction is regioselective, and what we observe is Markovnikov regioselectivity. So I'm going to say Markovnikov. So, and what that is that, let's draw the hydronium more explicitly, showing the three hydrogens. So just going to do a slight change here. So instead of drawing the H3O plus, I'm going to do this so that we explicitly grab the pi electrons acting as a base. These electrons are going to be assigned back to the oxygen. And this happens Markovnikov because we want to, that way we add, Markovnikov means you add the hydrogen at the least substituted carbon, this side, so that you form the more stable carbocation, which is that. So that's what we mean by that regioselectivity. So now what happens in the second step is what we have is a nucleophilic attack. By what? Our nucleophile here, if you are under acidic conditions, essentially you have hydronium and water. So the species that acts as a nucleophile is water. Now, here, the geometry of the carbocation is trigonal-planar. The carbon here in the center is sp2 hybridized. So I'm going to change the geometry a little bit because I want to make this groups different. And the point is that when I attack with water, I have a chance to form two enantiomers. Because they attack, the nucleophile can attack from either side of the plane. As we said, this is trigonal-planar. So now, the product of that reaction is two enantiomers. So we're going to draw now. I can have, say, this. Well, in the first instance, we are going to have water like that after the nucleophilic attack. And then, of course, we need to remove the extra proton. And because we only have hydronium and water, remember that those are the species that we have. Here in this step, water acts as a nucleophile attacking on a carbon. Here, water is going to act as a base. And that way you will form the alcohol. And I'm going to change this so we can see better, I think. So now I will have this OH. But remember that the attack can happen from the other side of the plane. So I have that plus the enantiomer. And oftentimes we write it like so, En. And what that means is the enantiomer to that. So I'm going to switch these two groups and to draw the enantiomers. So essentially it will be keeping the isopropyl here. I'm going to change this too. And here is the enantiomer. So this is that, right here. So again, the hydration reaction then, in summary, happens under those conditions, Markovnikov. And so what it is that we are going to attack here with the pi electrons, get the proton. The hydrogen gets added to the least substituted carbon to form the more stable carbocation. Second step is a nucleophilic attack. Your nucleophile here is water. And then you form has an extra proton, so you need a proton transfer step. Here, water is acting as a base. Remember the difference. As a nucleophile, as a base is abstracting a proton. Removing that proton will give you the alcohol, but since This is trigonal planar. You can have the attack of the nucleophile from either side of the plane, and you can form two enantiomers. So essentially, let's say that it's about 50-50, so this is a racemic mix. If you're forming a chiral center, it may not be the case if the substituents are the same. But I wanted to show you that this is the stereochemistry, the outcome when we do a hydration reaction and we create a chiral center. We will do more problems on that.